Hi, this is Jeff Perry, and I'm the WEBENCH team manager. Today I'm going to show you a new piece of software that we have called the WEBENCH FPGA Architect. WEBENCH is actually divided up into several different tiers. The lowest tier and the most versatile is the WEBENCH Power Designer. And so what I'm going to do here is I'm going to give you a preview of that, or a review, I should say, of that and how that works. WEBENCH is actually a four-step process, beginning to end. First, you choose a part by entering your specifications for your design. You're normally presented with a listing of options for different parts that you can use in your power supply. The second step, you create the design, and here the BOM is created, including all the passive components and other things that are required to make the thing actually work. Lastly, or I should say step 3, you've got the Analyze a Design step, and here you can do simulations such as SPICE simulations, and you can look at dynamic electrical behavior such as load transients, line transients, startup. You can also do thermal simulations with many of the parts. And the last step would be build it, and this allows you to get a custom prototype kit shipped overnight for those parts that have it. Not all parts have build it or thermal simulation. How do you access WEBENCH Designer? Go to www.national.com and click on the WEBENCH panel on the right. There's a tab that says Power, and there you can enter in your voltages and current and start your WEBENCH design. Or if you have a specific part that you'd like to use, you can go to the product folder for that part and then create a design using that specific part. Okay, once you started up WEBENCH and entered in your input voltages and current, you oftentimes will see a list, you will see a list of possible voltage regulators. If there's a voltage regulator in there that you think you should have gotten, but you can't see it, you click on the Why Other Parts Were Not Found button, and that will give you a listing of possible reasons why your voltage regulator was not found. For example, your duty cycle exceeds a maximum limit. So if your output voltage is very close to your input voltage on a buck regulator, you may have a duty cycle violation. This is kind of one of the more advanced features of WEBENCH. Once you've chosen your voltage regulator, you then go in and the software creates the design for you. And this is a view of the WEBENCH dashboard. Here you can get things like operating values charts, where you can look at efficiency versus current and voltage and other key parameters. Of course, you can look at the schematic. You can do design optimization, where you can design the power supply. You can optimize the power supply for high efficiency, small footprint, or low cost. You can look at specific operating values, efficiencies, currents, power dissipations, and other key information. You can go into the BOM and change components. And so if you have specific component vendors that you want to use, or specific custom components that are not in our database, you can enter them there. And then in the lower right, you can do build it and get reports on your design. Also to do build it, you can click on the shopping cart icon in the upper right. Okay, I talked a little bit about design optimization. What is design optimization? Well, we have a thing which we call the WEBENCH Optimizer dial, and that's shown here at the lower part of this slide. Above that is a graph of efficiency and footprint on the y-axis, and on the x-axis it's the optimization factor. So if you turn that knob, right now the knob is set to the 3 position. That's kind of a neutral design. In that position, we try to choose a balance of efficiency, footprint, and cost, and with a bit more of an emphasis on cost at that point. As you turn the knob over to the right, to the 5 position, that slider on the graph is going to go over to the right, and the efficiency, which is represented by green in the graph, goes higher. So at the 3 position, for this particular design, the efficiency was 90%. We can get it up to above 92% by turning the dial to the right. How do we do that? Well, we typically lower the switching frequency, and we choose lower resistance parts. Now, the side effect for that is, as we lower the switching frequency, we're typically going to have a larger inductor, because our inductance is going to have to increase to maintain the same kind of inductor ripple current. So as our inductor increases, our footprint increases. And you can see that trade-off here with the orange part of this graph. We've gone from about 350 square millimeters footprint up to over 1,000 when we go to position 5. If you want to go small footprint, on the other hand, you can turn the knob dial to the left and go to the 1 position, and the footprint goes way down to below 300. However, our efficiency also drops. And this is because we're now using higher frequency, higher switching frequency. And this allows us to get that inductor size down because we don't need as much inductance to maintain the ripple current. But we also increase our switching losses, our AC switching losses in the MOSFET. And so our power dissipations go up and our efficiencies go down. So in this particular design space, we've got a range of efficiencies from below 88% to above 92%, but we've also got a range of footprint from less than 300 to above 1,000. So this gives you the opportunity to go in and optimize the designs for what you need. What's important to you? Footprint, efficiency, and cost is also another factor. Okay, so just to summarize what I just said, footprint, efficiency, and cost are somewhat at odds with each other, along with performance, and they need to be balanced for a designer's needs. And design tools like WEBENCH will allow you to optimize this and select exactly what you need and the trade-offs you want to make. Okay, let's take a little break here. We're going to have a hands-on exercise, and so what I'd like you to do is fire up your WEBENCH tool. You can pause this presentation. Your management has requested that you use the LM2596 part since it was used before and it's a proven part. So create the following design emphasizing a balance between footprint and efficiency. Your input voltage is 14 to 22 volts, your output voltage is 3.3 volts, and your output current is 2 amps. And so what I'd like you to do is look at the system that has the smallest footprint, the highest efficiency, and the lowest cost. And you can do that by using the optimizer dial. And write down those values, okay? And again, using the 2596 specifically, probably the easiest way to do that is to go to national.com and search for that part number. And that will take you to a panel that will let you fire up the WEBENCH design. Okay, when you're done with that, come on back to the presentation and we'll pick it up. But make sure you write down those values. Okay, now that we're back, let's talk about the WEBENCH Visualizer. This was a tool that was released recently that allows you to visualize the possible results that you have for solving your power supply design. Okay, what this does is instead of just choosing one part at a time, this lets you look at multiple different parts at once. And for example, National has many possible solutions for a wide variety of different voltages and currents. And so for example, here we've got 14 to 22 in, 3.3 volts out at 2 amps. There's 50 different possible solutions for that. And so what we did is we created a tool that creates all those designs at once, well, in about 2 seconds, and presents those to you in a form where you can look at some of these trade-offs. The recommended solutions is in a table there on the right, and there's a chart on the left that actually shows graphically what's going on. The three most important columns, or very important columns on the table on the right, are the BOM footprint in square millimeters, the BOM cost, and the efficiency. And so for each one of these designs here, we've calculated those numbers for you in advance. And so this is not just the IC footprint cost and an estimated efficiency. This is an actual calculation of those values, including all the passive components in the design. So if you go to the left side of the screen there, you'll see the visualizer chart, advanced charting. If you click on that little box there, that will expand the chart to a larger size. And so here you can look at different trade-offs in your design. If you hover over a bubble in that chart, you'll see more details, including the efficiency, footprint, frequency, and the cost. You can also look at the bubble size, which tells you the BOM price. So the x-axis here is efficiency, the y-axis is footprint, and the bubble size is your BOM cost. So you can see 3 different dimensions at once. Also, if you want to zoom in on this, you can click and drag your mouse. Lastly, if you want to change some of the parameters, like let's say you want to plot efficiency and footprint versus frequency, you can use the drop-down menus to change the graph parameters. Okay, why are these solutions different? Here's a graph where we're looking at efficiency on the x-axis, footprint on the y-axis, and I've kind of broken out here what's happening. In the upper left, we have some devices that are older technology. These are over 20 years old, and so they have relatively poor efficiency and high footprint. Now, as you get into the middle section there in the orange, you've got asynchronous integrated switch devices. These tend to be relatively easy to use. And so they've got onboard MOSFETs, and typically they're simple, but they're kind of a balance between efficiency and footprint. As we move over to the right and we see the yellow highlighted areas, these are synchronous integrated switch devices. And so what these have is 2 MOSFETs on board, and they get higher efficiency. And then as we go down to the right, we see synchronous controllers, and so these require external MOSFETs. They tend to be a bit more complicated to design with, but if you want real high performance and high efficiency, those might be a choice that you might want to consider. So let's take a look at what we got here for this particular set of voltages and currents. On the default optimizer dial setting of 3, it shows the LM22676 device, and it had 80% efficiency, which is kind of in the middle, 228 square millimeters, but it had a price of $2.91, which is relatively low for this particular range. The smallest footprint got all the way down to 94 square millimeters, but we took a hit on our efficiency now. We're all the way down to 72%, and the cost is about $3. For the high efficiency, we've got the LM3150 controller, which got all the way up to 93% efficiency, but our cost went up, $795, and the footprint went way up to 969 square millimeters. So what this basically allows you to do is compare different designs up front before actually creating them. And that can achieve better results than just optimizing one part, choosing a part in advance and trying to optimize that part for high efficiency or low footprint or low cost. Okay, let's take another break here and do another hands-on exercise. The design problem is going to be the same one that you did before, except that now I would like you to see if you can find a better part than the 2596. So take the same input voltages, 14 to 22 volts, 3.3 out, and 2 amps out. That's 14 to 22 in, obviously. And plug those in and see if you can get a better result. Now you can do that by hitting the new icon in the top navigation bar of WEBENCH, and that will, and then click the Power tab, and that'll let you redo your inputs. So now what I'd like you to do is write down the system with the smallest footprint, highest efficiency, and lowest cost, and let's see if you can beat the 2596 with another device. Okay, we're back now. Now what I'm going to show you is the new Power Architect and FPGA Architect. The FPGA Architect specifically is a new tool that lets you do entire power supply systems designed around FPGAs. Now, as you probably know, FPGAs oftentimes require multiple loads, and which also require multiple supplies. This particular example is a board that was designed at National Semiconductor around an FPGA. It's got a core supply, it's got some IOs, a VCCA, flash, SDRAM, a CCD load, a PLL load, motor control, and miscellaneous load. And so what this breaks down into is 9 different loads and requires 5 different voltages. So how would you normally go about designing this? Well, you'd have to pick out each one of those loads, design a power supply, and then figure out how to hook those power supplies together. Do you want an intermediate rail? Do you want to go directly in from your input voltage, or what? So what we've done is we've created a tool called Power Architect. And what this allows you to do is simplify this process dramatically. First, what you do is you input your source voltage, and you see that there on the top of this slide. Next, you click on the Add Loads button, and that allows you to add arbitrary loads to your your system. And then you would click on the Submit Project Requirements button in the upper right. Now, specifically for FPGAs, you would click on the Add FPGA Load Assist button. Now what this does is that this pops another dialog up that gives you a listing of different FPGAs from the major vendors. And you can click on that FPGA and it will give you a list of pre-configured loads. And you see that over on the right side there. Now this includes all the loads that come, the VCCA, the VCC-INT, different IOs, PLLs, and these may have specific requirements. So here what you do is you'd pick your voltage and then click on the Add button. And then you get to a screen that looks like this. And so what we see here is that there's some of these loads have very specific requirements. For example, the maximum ripple allowed on the regulator, whether it requires a filter, a specific filter for that load, whether it requires a totally separate supply, and whether it requires a soft start. Also, here you can change the load current, which oftentimes you might do by going to one of the power estimator spreadsheets. And this is an example of a power estimator spreadsheet where it gives you the different load currents that are estimated for each load in the FPGA. So what you do here is you basically just copy these, type them into WEBENCH, and you can get the FPGA power supplies. Okay, once we've configured our loads, WEBENCH is going to go in and try to pick the best solutions. And so here's an example here where we've got 48 volt source input on the left. We have an intermediate 12 volt rail. And then downstream of that, we have a load that's hooked right up to the 12 volt rail. That's the motor control. And our other point of load controllers or power supplies are downstream of that 12 volt rail. Now, each one of these power supplies may have multiple different solutions to it. As we saw earlier in the visualizer section of this presentation, there might be up to 50 different supplies. And so what we do here is we calculate all 50 of those supplies, and depending on where your knob position is, your optimizer knob, we will pick the best solution for you. So what you're presented with here on the next step is the optimize step. And you've got on the left side is a bubble plot, or a chart, I should say, and that's got efficiency in the x-axis, footprint on the y-axis, and the bubble size equals the price. If you click on a bubble inside there, it'll highlight one of the architectures, or you can click on the row in the table in the middle, and the architecture is displayed on the right side of the screen. Let's take a look at several different possible architectures. And when I say architectures, what I mean here is how do we connect up the point of load supplies with the input voltage? So in the upper left there, we see we have no intermediate rail. We go right from our input voltage, 48 volts, down to our separate point of load supplies. And we have 1, 2, 3, 4, 5 different supplies. And they're all coming in from the left. Now in this particular case, it happens to be the lowest cost, but it's got the lowest efficiency and also the highest footprint. And reasons for this could be that, for example, if you're coming from a relatively high input voltage, each one of those supplies is going to have high voltage caps, and that can cause problems. It may be actually more effective to take an intermediate rail, have that one connect up to the high voltage with high voltage caps, and work off of that. And for example, we see that in the 12 volt option there in the lower left. That one's got a little better efficiency, a little better footprint. And as we move over to the right, we get some more complex intermediate rail architectures, and where we have multiple intermediate rails with different voltages. And finally, we see the one in the lower right that has the highest efficiency and the small footprint actually has a 12 volt rail and a 5 volt rail on it, intermediate rail, and the point of load supplies come off of that. So bottom line is you can look at this plot, and without getting into all the architectures in too much detail, you can quickly see which one of these guys is going to work best for you. As we have with the visualizer tool, we have the optimizer dial. And as you turn that dial, you will see different options appearing on the visualizer graph. What we do here is for each dial segment, we put it in a different color. So for example, at dial setting 1, those are listed in purple, and those are kind of down in the lower left portion of this graph. And as we move up the dial settings up to 5, that's in dark blue in the upper right. And so you can see here again this typical dispersion where you can either have high efficiency at the cost of high footprint, or you can have a small footprint but at the cost of lower efficiency. And the price of the BOM, of course, falls in with that also. In this case, remember now that we're talking about the entire system. So this may be 5 or 6 different power supplies all added up together. And so you're really optimizing your entire system rather than each supply individually. Okay, for our example here, let's see what we came up with. The lowest cost was $14.68. The smallest footprint was 1,635 square millimeters, but our cost went up to $19. And those are both in the 85% efficiency range. If we want high efficiency, we can get all the way up to 91%, but our footprint's going to go up to 7,100, and our cost may go up to 4,159. And so maybe that's, if you really need high efficiency, you might be willing to pay that, but maybe there's a compromise somewhere in between those two. And so this tool allows you to look at those types of compromise trade-off situations very quickly. Okay, once you've selected one of your architectures, you go into the next step, which is our view edit step. And here you get a close-up view of the power supplies. And as you click on a different power supply, or each power supply, you can see its contribution in the pie charts there on the right side. There's a pie chart for power dissipation, BOM price, and footprint. And so if one of the particular supplies is a major contributor, let's say, to power dissipation, and you're very interested in high efficiency, you can click on that supply and then click on the alternate solutions tab in the lower right there, and perhaps choose another IC and fine-tune that a little bit and try to get closer to your goals. So after you're done with this step and fine-tuning, you click on the Create Project Designs green button in the upper right. And what that does is it creates the entire power supply project. We call that a project, and that's a collection of all the power supply designs in your design. So here we have 5 different power supply designs. On the left side, we've got the system block diagram. And as you click again on each one of those blocks, it will pull up the WEBENCH design on the right side, and you can use the normal WEBENCH simulation, bill of materials management, and build it steps to optimize your design. So let's see what we got here. Within 2 minutes, using FPGA Architect, we have a power supply for all of our loads. And we got 84.9% efficiency, 2,149 square millimeters footprint. There's 64 components, and it's a $14.76 BOM cost. So you can see here that within a very short time, we have designed a fairly complex power supply system that actually works and achieves our particular goals. All right, so our hands-on exercise number 3. We're going to be using the FPGA Architect. We're going to have a source voltage of 22 to 26 volts. We're going to have 2 custom loads, a hard disk drive load at 3.3 volts and 0.5 amps, a memory load at 2.5 volts and 1 amps. So you'll add those in by clicking the Add Loads button. Then we're going to go ahead and add in an FPGA. So you'll click on the FPGA Loads button and select this particular FPGA and configure the voltages and currents as mentioned here on this slide. And so what we'd like to see is what is the system with the smallest footprint, the highest efficiency, and the lowest cost. And please write those down. Okay, we're back. I'd like to summarize what we've looked at today. First of all, we looked at the normal WEBENCH, which is a way to design a single power supply given a particular part number. We looked at the WEBENCH visualizer, where if we don't have any particular bias towards a part number, we can view up to 50 designs at once to get the best solution for a single power supply. Each design is optimized according to the knob setting that you've specified, efficiency, cost, and size. The WEBENCH Power Architect takes that to another level where we design entire power systems using the visualizer technology. And this is used for complex multiple load applications. It provides you with different rail architectures, not just the power supplies, but how are those power supplies hooked up to your input source. And then each system can be optimized at a system level for efficiency, cost, and size. And then what we've recently just introduced then is our new FPGA Power Designer. And this gives you pre-configured FPGA loads, including your noise and filter requirements. And so overall, in summary, hopefully what we've seen today is that WEBENCH saves you time. And I encourage you to use WEBENCH for your next design. Thank you.